Now we've gone through the various different structures of the eye, we need to look a little more into the functionality of how it all works. Now, refraction and lenses. Because your eye has the lens, which is going to be basically a rounded surface, anytime light is passing from one substance to another, so one transparent object to another, air, lens, vitreous humor, aqueous humor, all these different transitions will end up causing the light to change speed and kind of bend a little bit and change direction. So the whole point here is, as it comes into your eye, you're trying to focus it. So as light passes through a convex lens, now convex lens is the same as what your lens in your eye is. So that convex lens, kind of like this, as a light passes through, it's going to converge on a focal point. So the whole entire purpose of your lens is to make sure that it focuses on one sharp point. So you're trying to make sure you have that point of highest visual acuity. Now, sure, you can see things in your periphery, but if you notice, they're not quite as sharp as the focal point in the center. So when a convex lens forms an image, though, here's the interesting part. It's upside down and reversed right to left, which means what you're seeing in the upper right corner, your brain is processing in the lower left corner upside down. I know that sounds a little weird. Try this. The lens is in the middle here. This is your lens. Now let's say you look at the yellow box down here. That yellow box goes to the other side up here when your brain processes it. So you're taking everything and flipping it upside down and rotating it right to left. Now in this image, you can see that looking at a house and some trees. The left eye, you can see, is going to come and cover the left side here, but not get all the way to the right. It only covers a tree or so. So when you're looking at the actual image that left eye is bringing in, you'll notice that it's upside down and it's reversed. So you have to take what both the left and the right eye bring in, send that back into the occipital lobe, remember that primary visual cortex, and you end up with this view right here. You'll notice that the house is flipped right to left and it's upside down. Well, you're saying, well, hold on, then how do we know we're not walking on the ceiling right now? Because remember, there's the visual association area. It's going to interpret what you see and kind of correct this lens issue. So it knows that your feet are on the ground, for example, and you're not walking on the ceiling. It's all based on the brain processing the image, not just taking this raw image like this. But just a pure lens like our eye is, this is what occurs. But with our brain, it takes this, flips it back right side up, and back right to left, making sure we're seeing the proper image of what's in front of us, not some distorted image upside down and reversed. All right, so how does the eye focus again? Because we mentioned before, the lens is what changes things. Now, the lens is going to help us to see far, see near. It's all based on shape. You notice in distant vision, the lens right here is pulled by those ligaments, which means it's flattening out the actual lens itself. So therefore, can I think of it this way, is it has a flatter surface, not totally flat, but it's a flatter surface. The light doesn't refract as much as it comes through a flatter surface. Which makes sense because seeing far away, the light's pretty much on a straight line coming in as it is. But seeing more close up, notice how the lens gets more relaxed and gets a little bit thicker. So by taking that flatter one from the distance and making it thicker, there's more curvature. There's more refraction as the light comes in. Which also makes sense because if you think about it, right in front of you, that light has to bounce and hit the eye and come back down to one point. So it kind of looks like this and how we can correct it if there's issues. Normally the light simply goes right through and focuses in the back. The main focal point is that plane right in the back of the eye. But now if you're farsighted, hyperopia, that means that you've got a little problem where you're focusing behind the eye itself. By focusing too far back, when the light hits the back of your eye, it's not a point. It's still not where it should be, so it's a little fuzzier. The worse it is, the further back it's focusing. Thankfully, corrective lenses allows the light to be readjusted a little bit first and then readjusted again after that. So that corrective lens helps to make sure it hits your actual lens at the right angle to focus on the back of your eye. Now, nearsightedness or myopia, in this case, the focal point is too far forward. You'll see it's focusing up here, which means by the time it hits the back of the eye, it's starting to unfocus already. So again, corrective lens, it helps change the angle of light. Change it just a little bit so when it hits your actual lens, the lens then has the right focus to the back of your eye. So farsightedness, you have focusing points beyond the eye. Nearsightedness, you focus in front where the eye should be. So two things that thankfully quite often can be corrected within certain limits. So a little bit about the eye and how the light is focusing and refracting on the lens.